So this is a short discussion on continuity. So yeah, so up to now we've talked about over the last couple of units, asymptotes, vertical asymptotes, x approaches, a finite number in the graph may go to positive or negative infinity. Like if you're dividing, as x goes to like some point A and the denominator is zero at that point. And then for the horizontal asymptote, you get, as x goes out to positive or negative infinity, and then we might get a horizontal asymptote. Okay, so now we're going to talk about continuity. Some of this is really great if you're a math major. I'm not going to, you usually get, math 250 students aren't asked to memorize a lot of definitions. So it's a good idea to have some general idea of what these things mean. Okay, and so we've talked about one-sided limits where, if the limit of, let's say the limit of f of x is x goes to from the right to some point A, and then, we've talked about the limit of f of x going to A from the left. And if they're the same, we say that the limit as x goes to A exists. So that's, I think, actually section 2.3, or earlier sections. Okay. So, and sometimes you can find these limits with direct substitution. Sometimes we look at the graph. Um, so let's just talk about there in that box. There's like a star there. No, I'm drawing a line. Okay, so formally, and again, this is what I'm saying. To me, okay, what does it mean for a function to be continuous? It's this informally, right? This is way I always think about it. So students, this is way, at least start with this. A function is continuous on an interval if the graph can be drawn without lifting your pencil. So let's say there's no jumps, there's not piecewise discontinuities, there's no holes in it, there's no asymptotes or anything like that. So if you can just draw the graph and without lifting your pencil, that interval that you drew is, the function is said to be continuous here. So a function is continuous means I can draw the graph without lifting my pencil. So that's the kind of I think probably what a lot of us think of it as. Okay, but here's something a little bit more formal. So a function's continuous at some point C. Well, first of all, f of C has to exist. So we've seen problems like there, like we'll see, we're going to go to those examples, but maybe there's just a hole in the function. F of C just isn't defined. It's defined on either side of C, but it's actually not defined there. The limit from the left and the limit of going to the right to C has to exist. It has to be the same point L. So functions continuous C if f of C exists. The limit as x goes to C of f of x exists, right? So the limit as x goes to C from the right and the limit as x goes to C from the left are identical. And then also, most importantly, that limit L happens to be f of C. So so f of C exists. The limit of as x goes to C exists and is equal to f of C itself. Okay, so let's look at some of these really great examples here. Okay, so there at this point C, well, f of C, rule one automatically fails, right? F of C, DNE, it's DNE, students. It does not exist. Okay, so automatically you can say the function's not continuous there. Now there's something called removable discontinuity. All you have to do is, in this case, the limit is x goes to C from the right and the left are the same. So you could just define f of C to be that limit. And then you have what's called the remove. So there you have a removable discontinuity. It's possible to actually define f of C such that the function is continuous. But you can't actually draw that graph. You have to take, if you're going to draw this graph there in one with the hole in it, you have to take the pencil off the paper. So here's another one, 2 and 3. Oh, we have to take our pencil off the paper to graph. Well, so 2, this is like a piecewise discontinuity, or piecewise continuous, I'm sorry. So you got these two graphs, and at C, we jump up, and then we continue on. So we take so as we're going from left to right at C, we jump up, we take the pencil off the paper, jump up, and continue on with the graph. And for C, okay, what happens is you get to C, you just jump up briefly, and then you go back to kind of where you were before. But once again, you have to take your pencil off the paper, and in the limit in each case, the most important thing, students, the limit, like here, the limit of f of C, the limit of f of x as x goes to C doesn't exist because the limit from the left and the limit from the right are different, right? So there's the problem. And so here the limit does exist. the limit as x goes to the right and as x goes to the left exists, but that limit is not f of c. So we've seen, so these are the three cases. F of c just isn't defined. That's the case here. The limit as x goes to c doesn't exist, right? This doesn't exist. It exists as we go from the left or the right, but those limits aren't the same from the left and the right. And the limit as x goes to, the limit exists, but is not equal to f of c. And then, so if a function is continuous at some point c, if we multiply, there's a bunch of rules, students. It's kind of intuitive. We use them all the time without thinking about it. And then we're talking about this box right here. If you multiply, so if a function is continuous at a point c, and also g is continuous at a point c, well, if you multiply by a constant, that b times f is still continuous at c. So again, these two functions, f and g, are continuous at c. You can take their sum of the difference and that's still continuous at c. So like polynomials are always continuous. Like the individual terms like x and x squared are continuous everywhere, essentially. And when you add them together, they're still continuous. The product of two continuous functions at a point c is continuous at point c. The quotient is also continuous, assuming g of c is not equal to 0. And then the composite of the function is also continuous. If g is continuous at c and f is continuous at g of c, then the composite function f of g of c, f of g of x is continuous at c. And that's kind of hard to say, so I will. I'm not going to try this again. Okay, so well, here, students, let's look at one. So we have the quotient. So polynomials are continuous everywhere. So x squared minus 4 is continuous everywhere. X plus 2 is continuous everywhere, but x plus 2, but x plus 2, that function is going to be 0 at x equal to negative 2. So we say this function is continuous everywhere except x equal to negative 2. Right, because you can't divide by 0. So actually, if you graph that near x equal to 2, you're going to get a you're going to get a vertical asymptote. Okay, the sine and cosine, like this number 2, yeah, again, the drawing rule. Can you draw without lifting your pencil? Well, we can draw cosine of x and sine of x. The other ones you can't. Remember, there's 6 trig functions. Sine of x and cosine, we can just graph them on a graphing calculator, some other graphing utility that you may have. I like Wolfram Alpha online. But the graph of cosine of x and sine of x, yeah, you can draw that forever without lifting your pencil. It's not true for tangent of x or cotangent of x or secant or cosecant. You get a vertical asymptotes. You have the other 4, you have to lift your pencil because you're going to be dividing by 0. Right? Like tangent is sine over cosine. So you get these vertical asymptotes wherever cosine is 0. So all the odd multiples of pi over 2, tangent of x is not continuous. Just graph the tangent function in your calculator and you see all the branches and you see all the vertical asymptotes. And I think I said this a couple of days ago in one of my lectures, my tape lectures. It's a good idea to know what the graph of tangent and cotangent look like, and also secant and cosecant. So here's kind of a fun problem. So it's a piecewise continuous function. Now, is it continuous? Lines are polynomials. So, but is this continuous where you get these breaks? So, like, is it continuous at, right? Like here. So we know it's x equal, for x less equal to 0, the function is just 3. And then the next function, when you go from 0 to 1, it's minus x plus 3. So we see that for this one, the function is 3 at x equal to 0. So it turns out it's continuous at x equal to 0, right? So if you actually graph the function, it looks something kind of like that. Not my beautiful graph there. Okay, but then when you get to x equal to 1, it actually, the f of here, so at minus x plus 3 is at f equal 1 is 2, and but here the other function 3x minus 5 at x equal to 1 is negative 2. So there's actually a jump. there's actually a jump somewhere. So at x equal to 1, actually this, I agree with this. That went down a little bit too much. I apologize. Okay, so it should stop at x equal to 2. So x equal to 3, yeah, so x equal to 3, then at x equal to 0, it's minus x plus 3. And then at x equal to 1, you get this jump, it goes down to negative 2, kind of goes like that. So there's this discontinuity at x equal to 1, it jumps. Okay. Okay, so now 4, the square root of 9 minus x squared, well, that's just the upper part of the circle, x squared plus y squared equals 9. It's just the upper half of it. And so it turns out, yeah, the domain, I think it was in our first or second quiz, the domain is everything from -3 to 3. And it's continuous there. It's continuous at, from -3 to 3. So problem 5 is kind of a fun problem. Okay, so you have this piecewise function for x less than 2. It's the second degree polynomial x squared plus ax. We don't know what a is. And for x greater than 2, it's 2x plus 1. So what value of a would make that continuous? So we want the functions to be equal to each other at x equal to 2. So we know that for the line portion at x equal to 2, it's the value is 5. Okay, so then and as x goes to 2 from so we know that as x goes to 2 from the right, the value is 5. What value of a can we put in to make this 5 at x equal to 2? Okay, so when x is 2, what you get is 2 squared plus 2 times a, and you want that to be equal to 5, and you just solve, you get a equal 1/2. So if a equals 1/2, the function is continuous at x equal to 2. And then we have these terms removable, non-removable. And, I'm not asking you, I'm not suggesting you memorize this. A lot of times we forget, we learn it and then forget if you don't use it a lot. But there's 3 kinds of discontinuities. They're infinite. Well, if you're approaching a vertical asymptote, the discontinuity is infinite, and it's non-removable, meaning we can't give a new value to that function of the discontinuity and make it continuous. And then you have like a jump discontinuity. Let's look at the other one. There's a jump discontinuity is non-removable, and when there's a hole, it's removable. So it's visually, let's see, this would be better. So this one is not, here you have the jump discontinuity. You get to see, and you jump up as you go left to right. And so, and then at number 1, you have there's a hole there. And so, but you can actually, if you actually replace if you actually define f of c equal to the limit L, that would, then the discontinuity is replaceable. See, f of c isn't defined, so we can actually give f of c a value to make it continuous. Okay, so that's what, so the jump discontinuities are non-removable. Whereas when there's just a hole, it's removable. I'm not sure that's so important. Maybe there'll be some MATLAB questions on it, but okay. So then the famous intermediate value theorem. And again, this is if you think you want to be a math major, you want to know these theorems. You don't necessarily have to know how to prove them right now. But if you're going to be a math major, you should, that's my feeling. If you're a math major, you should like doing proofs. I mean, I was a math major, and I like doing proofs, students. So, but where I grew up in Michigan, it was really cold. You can't go outside a lot of times. So I just stay inside and learn how to prove theorems. Okay, anyway. So what it's saying is, okay, let's say you have a continuous function on an interval from A to B. And let's say as you're going from, and so let's say, at A, the second coordinate is f of A, and at B, the second coordinate is f of B. And let's say like in this picture, f of B is greater than f of A. What it's saying is that there's some, for let's say K is in between f of A and f of B. So let's say we have some K. This doesn't look good. So let's say K is in between f of A and f of B, that there's some C such that f of C is equal to K. That's what the intermediate value theorem tells us. And it kind of intuitively, it makes sense, right? Because you can't lift, if you can't draw the graph without lifting your pencil, and if f of A is less than f of B, the graph has to go through, there has to be some second coordinate equal to K. Okay, so now, and so here's so this theorem can be useful. So let's look at this function here, x cubed plus 3x plus 2. And it has we want to show that it has at least 1 0 on the interval -3 to 1. Did I? Yeah, so actually I plotted that down here. And actually I went more than -3 to 1, but you can see here, well, -3 would be about right here, and 1 would be about right there. And you can see it has to cross the line y equals 0. And so the whole idea is f of 3 is negative. See, f of 3 is negative, and f of 1 is positive. F of 1 is greater than f of 3. So as you go from so you go from that negative, you're drawing the graph, and you're going from that negative second coordinate to the positive second coordinate. Somewhere the second coordinate better be 0. Only if it's a continuous function, right? And so that's what the intermediate theorem tells us. The 0, it's some value of x less than 0 that makes f of x equal to 0. Okay, but let's go back up here and see how to. Yeah, so the intermediate value theorem tells us there's some point C in the open interval -3, 1 such that f of C is equal to 0. So let's just see how we solve it right here. Yeah, so basically to demonstrate that, first you plug in the endpoints. So here we have this function x cubed plus 3x plus 2, and we want to show that there's some number C inside the interval -3 to 1 such that f of C is equal to 0. And so first evaluate f of C, and it's 34, and you evaluate f of 1, and it's 6. 6 is greater than 34, right? And so 6 is greater than 34. So when you're drawing the graph, you're going from second coordinate -34 to second coordinate 6. Somewhere the second coordinate has to be 0. So there's got to be some point C in the interval -3 to 1 that makes this function here equal to 0. We don't actually know what it is, but we did prove there's a solution. Okay, so here's another one, x squared minus this polynomial on the closed interval 0 to 3. And we want to use the intermediate value theorem to show that there's some C such that f of C equals 4. We'll just subtract off 4 from the function, and what you prove is, so then you consider the function x squared minus 6x plus 12. So just consider this function. You can actually factor. You subtract off 4 and you factor, and you can get the solution. But you can actually, we want to prove that there's a solution to this function, right, to that equation right there inside 0, 3. Just subtract 4 from both sides, and you want to show that. Sorry, my printing is pretty bad there. You want to show that there's some solution from 0 to 3 inside the interval 0. You want to show that there's some solution in the interval from 0 to 3. So when x is 0, what do you get here? So when x is 0, you're getting 8, right? And then when x is 3, you're actually -1. So f of 0, I'm running out of room here. F of 0 is positive, and f of 3 is negative. It better be negative. So it's 17 minus 18. You get -1. So when you go from 3, you're drawing the graph from 0 to 3. You're starting at 8 and you're going down to 1. at some point, the second coordinate better be 0. So we know that in the interval 0 to 3, there's some solution to this equation there using the intermediate value theorem. And again, you just evaluate the function at the endpoints. And if one endpoint is positive and one endpoint is negative and the function is continuous, somewhere the graph has to cross the line y equals 0. But of course, this equation can easily be factored, so you don't really need the intermediate value theorem to prove what we just talked about. So let me just stop sharing here. Let me see, is that all I wanted to say? Yes, so there's my great plot, okay.